Hey everybody, and welcome to our final video on functions. In this video, I want to wrap up this topic by talking about a really cute topic called recursion. And to give you an idea of what it is, let me start with some philosophy, I guess. So here's a paradox. The paradox consists of three claims, all of which appear to be true. The first claim is that living things are machines. And when I say machine here, I'm using it like a biologist would. Okay, so this claim number one is essentially a tenet of modern biology, right? You can explain how things work mechanistically, right, through biological processes, through chemistry, things like this. So that's all I mean by machine right here, right? A living thing is a machine in that you can understand how it works mechanistically. Okay, the second claim is that living things can reproduce, basically, right? So think about an amoeba splitting in two, right? Or humans, of course, can reproduce with each other. But anyway, living things can have offspring, right? Okay, so this first claim is a tenet of modern biology. It's true, okay? If you accept modern biology as true. Claim two is like super obviously true, okay? Living things reproduce, right? Okay, claim three says that machines can't self-reproduce, right? Like a robot can't make a copy of itself. It's not an amoeba, it can't split in two or something. Okay, so all three of these claims, I think, are obviously true on some level, right? You can explain how living things work through biology or chemistry mechanism. Living things can make copies of themselves sometimes. They can self-reproduce like amoebas can. Machines, though, can't self-reproduce. Okay, there's a problem here, though, right? Living things can reproduce, but living things are also machines, and machines can't self-reproduce. Okay? So it's sort of a contradiction, right? Living things can self-reproduce, but also they can't. You've just immediately contradicted yourself. So you have three claims here, all of which seem to be true, and yet they can't all be true, right? Because if they are all true, you contradict yourself. So what makes this a paradox, again, is that all three of these things seem to be true, but they can't all be true. Something must have gone wrong here in one of these claims. Okay, so since claim one is basically what modern biology says, and we accept modern biology, and claim two is like super self-obvious, right? Again, I'm not saying that like you can split yourself into copies of yourself, but clearly there are living things that can do that, like an amoeba can, right? So claim two is obvious. Claim three, I guess, is the least obvious, and here, though, is an argument for number three. Why would that claim three be true? Well, consider a machine that constructs other machines, like you have a factory that's automated to produce a car. Well, it sort of stands to reason that the factory has to be more complex than the car that it's building because the factory contains the car's design within it. Right? That stands to reason. If the factory makes the factory must be more complex than the car because the factory has the car sort of contained inside of it. So to state this more abstractly, if A is a machine that produces machine B, A must be more complex than B. Therefore, A couldn't produce itself because a machine can't be more complex than itself. Okay, so all three of these statements seem to be true. Number one, biology says it's true. Number two is obviously true. And then I just gave you what I think is a pretty good argument for number three, right? You can't reproduce yourself because you can't be more complex than yourself. Okay, so we have a paradox on our hands. It turns out, though, that item three is false. Machines actually can self-reproduce in the way that, say, an amoeba can on some level, okay? Basically, machines can have themselves inside of themselves, okay? So this statement here is actually false, it turns out. Okay, so you would think that containing a car design inside of a factory means the factory is more complex than the car, but you would be wrong. That's actually wrong. So the idea of machine self-reproduction, it has lots of names. Recursion is one of those names. The idea that a machine, or in this case a program or a function, can feed on itself, can reproduce itself, can call on itself, that's the idea of recursion. Okay, so in particular here, this video is about recursive functions. So what would it mean for a function to be recursive? For a function to be recursive means that the function contains itself inside of itself. Just like a machine that produces machine B, right, actually contains B inside of itself, right? That's what a function would look like. That's recursive. So whenever you are introducing recursive functions, you always start with the most classic example there is. This is like old school, playing the hits or something here, the Fibonacci numbers. So if you don't know what the Fibonacci numbers are, here they are. It's just a list of numbers. They start with 0 and 1. And then beyond that, each number in the list is the sum of the previous two. Okay, so you start with 0 and 1. 0 plus 1 is 1. That's why there's a 1 right there. Okay, what's the next number? The next number is the sum of the previous two. 1 plus 1 is 2. That's why there's a 2 there. What comes next? Well, 2 plus 1 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And so on to infinity. Okay, you just keep doing this forever. So the nth Fibonacci number is the previous one plus the second previous one, right? The one just previous to you and the one twice previous to you. Add those two numbers together, that gets you the nth Fibonacci number. Okay, so let's write a function that takes n as an input and returns the nth Fibonacci number. So if I input 4, it should return a 2. Why is that? Well, because 2 is the fourth Fibonacci number. If we input the number 8, we should get a return value of 13. Why is that? Because 13 is the 8th Fibonacci number, right? 1, 2, 3, 4, 5, 6, 7, 8. The 8th Fibonacci number is 13. Okay, so what would such a function look like? Well, let me scurry on over to the compiler here. So let's call it fib. First of all, notice every number in this list is an integer. So you're going to get an integer back, right? The return values are things like 2 and 13. They are numbers in this list. So it's an integer function, and you're handing it an integer in that tells you which number you want from there. Okay, so what does this function look like? Well, notice I can just do some hard coding here. I can say, for example, that if n is 1, what should we give back? Well, if n is 1, you're saying give me the first Fibonacci number back. The first Fibonacci number is 0. So I'm going to say return 0. Okay, so far I haven't done very much. I've just said that, hey man, if I feed you the number 1, what I'm saying is the 1th or the first Fibonacci number, that number is 0. So please give it back to me. Well, what if I feed in a 2? What should I give back? Well, the second Fibonacci number, else if. The second Fibonacci number was a 1. So I'm going to return a 1. Okay, so again, so far I haven't done very much, but if I feed in a 1 or a 2, it will give me a 0 back for the 1, the first number. It will give me a 1 back for the second number. So back in main, I could say something like, hey, computer, what's the first Fibonacci number? Oh, yeah, so this compiler really does insist that you always return something no matter what. So let me just put this in here to make it happy for now. Okay, I'm not done building the function, but notice that if I don't feed in a 1 or a 2, okay, like if that's not there, right? If I feed in a 3 or a 4, it doesn't know what to return, and that makes it very unhappy. So just for now, just to pacify it while I'm making a point here, let me just return something else. Anyway, so if I feed in a 1 here and I run this, it gives me a 0 back. Well, that's what's supposed to happen because the first Fibonacci number is 0. If I feed in a 2, it gives me a 1 back, which is what was supposed to happen. The second Fibonacci number is indeed 1. Okay, well, what happens beyond that? Well, beyond that, now you can start this recursive process where you are taking the sum of the previous two numbers. So notice, right, when I say here that nth guy equals the sum of the previous two, that makes no sense for like this number right here. There aren't previous two numbers. There's only one previous number. So this definition right here doesn't really kick in until right here, the second number. Okay, now check this out. This is going to blow your mind. This is where recursion comes in. What should I do if I don't feed in a 1, I don't feed in a 2? In other words, I want to know what the third Fibonacci number is, or the fourth, or the fifth, or the seventh, whatever, right? Like if I feed in a 4, I should get a 2 back, right? Actually, before I blow your minds, let me just point out, I suppose you could do something like this. Well, you know, if I give you a 3, I want the third number, which is, 1. If I feed in a 4, I want a 2. That's the fourth Fibonacci number. You know, like, etc. You could do something like this. The only problem, of course, is that you would have to keep typing forever, okay? You can feed in any positive whole number here, right? So far you haven't made too much progress. There's an infinitude of typing left for you to do. So what you do is, you just say, well, otherwise, if the number is bigger than 1 or 2, what should you do? You should return, the sum of the previous two numbers. Boom. Okay. What have we created here? We have created a self-reproducing function, a function that has itself inside of itself, right? It has its own blueprints inside of itself so that it can recreate itself. It's actually quite philosophically interesting on some level, you know. I don't know if you find it interesting, but this pleases me, okay? This sort of massages my brain. But anyway, so let's talk through what happens here. If n is 1, I just give you a 0 back. We've already done that. If n is 2, I just give you a 1 back. Well, what if up here, let me make some more room here. What if right here I type a 3? What happens? Well, I come down to the function, n becomes 3, right? So n is not 1, n is not 2, n is 3. So I enter this else block. What I return is fib of 3 minus 1. Well, 3 minus 1 is 2, isn't it? Okay, and I know what fib of 2 is. Fib of 2 is defined right here. That's 1, right? The second Fibonacci number is 1, and I've taught the computer that. Okay, and if n is 3, what is fib of n minus 2? Well, it's fib of 1, right? So what you're literally saying is, if you put a 3 right here, you're saying, hey, give me back the second Fibonacci number plus the first Fibonacci number, and the computer knows what those are because you taught it that, right? These 4 lines of code here taught it that. So when I press run here, it gives me a 1 back as it was supposed to, right? 0 plus 1 is 1. Okay, what if I put a 4 right here? Well, down here in the function, n becomes 4. Well, 4 is not 1, 4 is not 2, so what happens? You enter this block right here, okay? So what happens is you return fib of 3 plus fib of 2. Now, fib of 2, the function already knows what that is. You taught it that by hard coding it, right? Fib of 2 is 1. What's fib of 3? Well, to find out fib of 3, the function just feeds 3 in and repeats the process. Okay, it just feeds on itself. So, you sort of set off a chain reaction here, and the result ends up being 2. What if you type in 8 right here, the 8th Fibonacci number? What happens? N becomes 8. You know, It's not 1, not 2, so into this block you go. So you return fib of 7 plus fib of 6. Well, how does the computer know what those are? Well, it just takes each of those separately, 7 and 6, feeds them into this function, repeats that process. It ratchets its way on down to something it knows, which are 1 and 2, and then it can build its way back up. So 13, which is what we said we should get. Okay, isn't that nice? That's really nice. So again, just to make this totally explicit, let's do something I haven't done yet, which is 5. Okay, how does the computer know what fib of 5 is? When we come down here, it's not 1, it's not 2, so into this else block we go. So return fib of 4 plus fib of 3. How does it know what fib of 3 is? Well, we've already talked through that, haven't we? Fib of 3, it just does fib of 1 plus fib of 2, which it knows how to do, because it knows 1, it knows 2. Okay, how does it know what fib of 4 is? Well, fib of 4 is fib of 3 plus fib of 2. It can handle 2, and it can handle 3 because it just handled it a second ago, right? So you're setting off this chain reaction, right? You're sort of just building your way up to 5. You know what happens for 1 and 2. You then know what happens from then on, recursively. So you just can ratchet your way up to 5. And out pops 3, which is indeed the 5th number. Anyway, so it's really nice. You've created a function that feeds on itself, that calls on itself, okay? Anytime you have a function that calls on itself, a function that has itself inside of itself, that's a recursive function. So in your homework for this section, when it says, write a recursive function that does whatever, you might be able to think of a way to get the function to work without recursion. Okay, but what I'm insisting that you do is write a function that calls on itself, like this example does. Okay, so that's sort of, again, old school, playing the hits sort of vibe right now. Yeah, this slide here is just explaining everything I said in English, okay? So if you'd like to, you can pause and read this, but I've already said all of this, so I shall proceed now. I want to give you one more example. It's an example you guys have done without recursion, but I want to show you how nice this is with recursion. So let's think about calculating the median of a list. Okay, something you guys have done before. Taking a list and finding the middle value. So first, let me just create a list to play with here that I want to feed in there. So I don't know, list of 0 is 4, list of 1 is 10, list of 2 is 9. List of 3 is 6, whatever. Okay. Let me take the Fibonacci stuff out. Okay, so the function itself, right? You want a function that calculates the median of a list. So let's call it median, and we're going to feed in a list. An integer list, I guess, is what we've decided on. Okay, so here's how the declaration basically looks, except, of course, we have to think about the return value. So as you guys have already thought through in previous homework, the median of an integer list may very well be a decimal. It depends on if you have to take the average of the middle two numbers. So I'm going to declare it as a float function, because the median can be a decimal sometimes. Like this list right here, I think the median is 7.5, right? Midway between 6 and 9. Okay. Now, for reasons that will become clear in a second, I'm going to pass this guy by reference. Let me now build this function recursively, and the way I'm going to think about it is as follows. One way you can think about calculating the median of a list is, and a couple of you guys actually thought about it this way, delete the first entry, delete the last entry, and then just repeat that process until you get down to a list of size 2 or size 1. So like this list right here that I've already created, I guess I should sort things first, right? So I'm going to sort list.begin, right? Because to find a median, you have to sort things from smallest to biggest. Okay, so there we go. So this list right here, when I feed it into this function, I mean, eventually I'm going to just do this, right? Tell me what the median of this list is, please. When I feed this list in here, oops, like not lost, list. Okay, when I feed this list in here, it has to sort, right? That's the first thing. And then one way you could think about things happening is now the list becomes, the computer's not going to like this, but let me just type it. That's your list, right? You can imagine just erasing the 10 and erasing the 4 simultaneously, right? You're only left with 2 numbers, so you should average the result. The average of 6 and 9 is 7.5. Okay, what if you had a list that looks like this? Okay, so it's an odd length list. To calculate the median, you could imagine erasing the 11, erasing the 4, erasing the 6, erasing the 10. You're left with just 9. That's the median. So again, the median is what's in the middle, right? So one way you could think about finding the middle is just repeatedly erasing the first and last entries until there's nothing left but the middle, okay? That's what this function will do. So the first thing it's going to do is just check if the list is small enough yet. So if list.size is 1, then we're just going to return that entry, right? Whatever's left, if you've terminated at size 1, that's the median. So again, if your list was this, 4, 6, 9, 10, 11, right? If that was your list, this process of erase, erase, and then again, first and last gone, right? Terminated at 9, that's the only entry left. So if you ever reach a list of size 1, just return whatever that entry is. Similarly, if you ever reach a list of size 2, you should return the average of the 2 entries that are left, just like a second ago, right? Like this 4, 6, 9, 10 guy. If I erase the 4 and erase the 10, what's left over now are the 2 middle numbers because the list had even size. And what I should do is just average those. So return list 0 plus list 1. So the 2 entries that are left divided by 2. Okay. Otherwise, what should I do? Well, otherwise, the list is still too big, isn't it? I haven't erased enough. So what I should do is list.erase, list.begin, delete the first entry, then erase the last entry. That last entry is at position size -1. Okay, so you erase the first entry, erase the last entry, and then what you do is just feed the resulting list back into the median function. Okay, here's the recursion. Notice the function's called on itself, right? So what's happening up here is, let's say my list is 4, 6, 9, 10, 11. Okay, I feed that list in. The first thing this function does is, since the list size is too big, erases the 4, erases the 11. It then feeds the resulting list back into the function. And since you passed it by reference, you remember these changes you just made. Okay, all changes are remembered. So the function sees this list. Okay, well, that list is too big. It erases the 6. It erases the 10. So you have a list of size 1 left. You feed that into the function. The function returns the only entry it sees. So again, it's like a chain reaction, right? You just keep doing this until you reach exactly what the function knows what to do, right? It either gives you the entry that's left or the average of the 2 entries that are left. So back up here in main, when I feed it 4, 10, 9, 6, the first thing that happens is you sort all of that, and then you do this cascading process. And let's just see what it does. Prints 7.5 as it was supposed to, right? So again, this list here, right, 4, 6, 9, 10, you sort it. That list has size 4, so you enter this else block. What does this else block say to do? It says to erase the 4, erase the 10, gone. Okay, now you take the list 6, 9, feed that list back into the median function. Well, now when you feed that list in, the size is 2, so now the function knows exactly what you want it to do. It just averages those two for an average of 7.5. Let me now just tack on a 5th entry here. The median of this list is 9. That's what's in the middle. So let's ask it to print 9. So anyway, this is really nice. It's like a snake eating its tail or something, a function feeding on itself. So the function contains its own blueprint inside of itself. It's nice. Okay, so that's what recursion is. That is the final topic of functions. So at this juncture anyway, we are done with material. We're done with new material. So what happens next is we spend a week on exam type stuff. So we review for a while, then we take an exam, and then afterwards we just use all of these tools in some really nice, creative, powerful ways. So we are actually done learning topics. We are going to spend the rest of our C++ time together applying the topics. It should be super fun. Okay, I'm excited about it. So see you in class.